So, hi, this is period 7, and we're going to be talking about your reading last night. You guys had the assignment to read sections out of chapter 6, and so I want to know, first of all, what is it that you learned from your reading?
Is this like posthumous exam stuff?
Yes, it is. Yes, it is. And that actually sends a message. And what the message that it sends is, an exam grade is of moderate importance. Actually knowing physics is of high importance. So tell me, Ben, what you learned from your reading.
The conservation of the potential energy from like 1/2 MV. What energy accounting?
Go ahead. Don't let him
Yeah,
interrupt you.
the equation 1/2 MV squared. I mean, yeah, plus 1 mgy equals 1/2 mv2 squared plus mgy2.
Okay. Now, you express this as conservation of energy. And there's some merit to that. Conservation of energy. However, I would call this an equation for a specific situation rather than a general equation. Now, why do I say that?
Because it doesn't work like spring or something.
Yes, that's exactly right. It works under what circumstance?
You're using kinetic potential energy that's not the spring.
Actually, it's more specific than that. It's potential energy from what force? Gravity. Gravity only. That's right. So this is actually conservation of energy for gravity only. Does that make sense?
Yeah.
And for that reason, I would actually not recommend memorizing. Instead, I would recommend memorizing the general equation. What is the general conservation of energy equation out of which this comes?
Plus V1 equals C2.
Exactly so. Or if you recognize that K plus U is the total mechanical energy of the object, we get E1, energy 1, equals energy 2. In other words, the total energy doesn't change for conservative forces. Good. What did you learn from your reading? Cyrus? Do you have a question about the reading?
I just read it and okay. Okay.
Cyrus has got it all under control. Okay. Moving on. What did you learn from the reading?
I just exactly same thing. I just learned exactly the same thing.
Did you? Or did you do the reading at all?
I'm reading it. That's not the problem actually.
Yeah, no.
I just focused on certain problems.
Don't do that. When I say do the reading, what I mean is do the reading. Here's why. Especially if you are learning this in a different language, and you are, you need the vocabulary. And the only way to do that learn that vocabulary, unfortunately, is to drill down into the details and do the hard work of doing the reading. You must. You will not survive otherwise. What did you learn from the reading? You must do the reading.
I did. Oh. Like, I don't feel like that funny. I just feel like
I didn't feel like running.
like Cyrus.
Yeah.
I read it. I didn't find anything.
We have a word for that. It's called skimming. And unfortunately, physics can't be read by skimming. You have to actually read.
Again. I read.
see. Eric, what did you learn?
Not much, but just basically that problem is much easier when I explore free-body diagram.
Ah, free body diagrams, a useful tool. What did you learn?
The original energy and spring.
Good.
Spring.
What is the potential energy for a spring?
1/2 is speed.
There you go. Good man. All right. What did you learn from the reading? You may feel that since English is your first language, that you're not in the same condition to see it, but actually physics is a foreign language.
Yeah.
And so you actually have to get down and do the reading. Make it so. Good. What do you mean by that?
You can take all the different forces and then turn them into X and Y components and then do the math that way.
Yes, you can. Good. Very good. Okay. Next thing is, do you have any questions about the homework problems that you did?
Like yesterday, I was reading stuff like actual return, so should I keep those materials for
Yeah, I would, and I'll tell you why. The final exam is going to focus on the second semester material, but the mechanics is all in the background of what we do, and so it doesn't really go away. It goes. Yep. Okay, homework questions. Who's got them?
Keyboard is true.
What was the most interesting problem that you worked on?
The most interesting ones I worked.
Uh-huh.
Well, 32 was just kind of fun because, well, Tarzan.
32 is funny because Tarzan. Okay.
But, I hadn't done a work problem in so long. It's just kind of interesting to do another one
Okay.
after so long.
The most interesting problem that you did then?
That wasn't very interesting.
Are you doing them late at night or something? Early this morning. Yeah. Yeah, sometimes when you have trouble managing the time, so you end up doing it non-opportune time. What that does is it takes a lot of the enjoyment out of it. It turns it into, oh, we gotta do this, because otherwise you're gonna fuss at me and lose problems and all that stuff. You know what I'm saying? So, encourage you to manage your time a little better, so that you get the optimal time for work as opposed to suboptimal time.
Yeah, I mean, you can choose. I mean, there's just the four issues on this.
And, right, you can do that. What's the cost of doing that?
Those are challenges.
You don't learn much, right? Which means things that are challenging continue to be hard for you, whereas what should be happening is they should be getting easier as they continue to challenge themselves. So, just keep that in the back of your mind. Most interesting problem? 38. 38. Yeah, so what was interesting about this problem? I like this problem.
It's fired upwards first.
I'm not going to do... They wanted the speed right up here at the top, am I right?
No, it's speed when it hits the ground.
Oh, right here at the bottom. So what was the
I actually
interesting...
did the one at the top, and I was looking for it. Yeah.
So what did you find that was interesting when you actually ended up solving it?
The accident
Yes. Not only the x doesn't matter, but also the angle doesn't matter, right? Because we're concerned only with the kinetic energy, and that's an interesting and profound idea. I could shoot it at any angle, and the answer would be the same. I can even shoot it downwards, and the answer would be the same. Really fascinating, isn't that?
Yeah, yeah,
Yeah.
I mean, it makes sense.
So we have 1/2 times mv0 squared plus mgh is the total energy here, equals 1/2 mv squared plus nothing is the total energy here. And my masses cancel out of the equation so that the final V is equal to the root of V0 squared plus 2GH, the end. And the angle just doesn't matter. Yes, it does. And one of the things I'm doing that makes it seem simple is I'm doing less numbers and more symbols. And by doing it in that way, it brings a certain amount of clarity to my answer. There's sort of a, I don't know how to express it, like a yin-yang thing, where if you express too much in terms of symbols, then the symbols just kind of clutter it up. But if you express it just in just the right number of symbols, it brings clarity to it. And here, by refraining from plugging in the numbers and just doing it symbolically, I can see what's going on with this thing. You see what I'm saying?
Oh, yeah, yeah, I just.
Most interesting problem you worked, since you went straight to the problems.
54.
Number 54.
Here's that.
Tell us about 54.
It has. We need to solve problems with cosine and sine,
Uh-huh.
and then it was kind of hard for me.
Mm-hmm. Yeah, it is a challenging problem. What we have here is a skier. Is it 12 meters per second? Is that right?
12 meters per second at an upward 18-degree incline.
It's an 18-degree slope, and he travels a certain distance. Is that right?
2 meters up along the slope before coming to rest.
Before coming to rest. So now they want to know what is mu.
Average coefficient of friction.
Yeah. Okay. Tell us about this problem. How did you do it?
We said friction force. MA.
Okay.
And then instead of friction force, we change U and G.
Here.
Oh. MA equal U and G. MA equal U and G. Okay. Oh yeah. Cosine.
Why? He jumped in the middle, and he didn't give us something really important. What was it, Eric? Oh no, what was it?
Free body diagram.
A free body diagram. You did not give us a free body diagram. How could you? We were counting on you. We need a free body diagram. What are the forces acting on our fellow skier here?
Friction force.
Frictional force, which way? This way. Like that. So friction is pulling him up the slope. Yeah. Are you sure you did this problem?
Although I just want to ask.
What other forces?
MG.
Pulling which way?
Huh?
Because as we all know, gravity pulls straight.
Yeah.
Straight. Yeah. Say it.
Straight down.
Thank you. All right, what else?
And one force.
Pointing which way? Okay, now what?
We should. The rotation force.
Are you positive you did this problem?
I didn't do that. I was getting. I tried to do that, but I just stopped.
Okay. You need some insight. Do you have an insight?
Yes.
What?
Forces.
Sum of forces. Not quite ready for that. Why? We need something first as a preliminary to sum of forces.
Different angle things for FM, or no, for MG.
What's the right word? Not angle
Cosine
things.
Theta.
Theta, or the MG
What's-
cosine theta, MG sine theta.
Now, what are those called?
Oh, the components.
Components. There we go.
I do
Different
know.
components. And what are those components?
MG cosine theta, MG sine theta.
Yeah, which one is which?
Sine's parallel to the surface.
Mhm. That's it. Okay. Now at this point, I need to interrupt your problem-solving process. Because I know where you're going with this. You're going to do sum of forces equals mass times acceleration, blah, blah, blah. You're working way too hard. This problem can be done in this way. You'll get there. But it is much more easily done by conservation of energy. Or by the work energy theorem is a better way of putting it. All right? So let's come back and do it in this way. Because we know already the final kinetic energy of the skier is 0. And the initial kinetic energy of the skier is 1/2 mv0 squared, right? And we know a number for v0. And now let's consider all of the work that is done on the skier by all of these different forces. First of all, the skier is going this way. So the work done by the normal force is 0. The work done by friction is going to be equal to negative force times distance. Negative because the angle is 180 degrees. And the work done by gravity can be computed best with the change in the potential energy due to gravity. As the skier goes up a height h, so that the potential up here is mgh, right? And it's pretty obvious that that h is the same as d times the sine of the angle. So I can say that negative fd plus mgd sine theta equals the change in the kinetic energy. And now we've accounted for the work done by 1, 2, 3 different forces, and we're done. We've got an equation here. solve for F. And here I know that we have numbers for a lot of these, but I'm going to keep it in terms of symbols. Divide both sides by negative d. Like so. And now we have a frictional force. And as we know, the frictional force is equal to mu times the normal, not mu times mg. You've gotten into a sloppy habit of thinking that the normal force is always equal to mg, and that's false. Here, because we are on an incline, the normal force will be equal to mg cosine theta. Yeah? And now you can see that my masses cancel out here. And I get mu. Wow, I need space. Mu equals g b sine theta plus 1/2 b squared all over d g cosine theta. Probably I wanted to leave numbers in here because I don't get a whole lot of enlightenment from this result. I get some, but you see where this goes. And you can see that the equation is much, much, much easier to set up from here. Here? Well, how?
You have G variables in common, D variables in common. And
That's
sine.
not enough. That's not enough. Having variables in common is not enough. If you are dividing, then you must not have variables in common. You must have common factors. Common factors. So that G or D would have to be a common factor of all of these terms here in order to cancel. And the reason for that is very simple. Division is the inverse operation of multiplication, and not of just anything. If I were to distribute like this, which I can do, because division is multiplying by the reciprocal, so I can distribute a 1 over g d cosine theta. Now I have common factors in this term only, and I get tangent theta plus v0 squared over 2 gd cosine theta, but there is no advantage to this, really. We didn't gain any insight from this, except to see that if the initial velocity is 0, then that would give me mu equals tan theta, which is the expression we got for the force on the cart. Okay? More work needed, I think. Interesting problem. Uh-huh.
Well, I don't know why, but 36 made me think for a second because like the thing it was asking was usually not normal.
Okay. Tell us how you ended up doing 36.
So after I just thought about the conservation of energy, it just made it so easy
Good.
because I just set up that 1/2 mv1 squared plus mgy1 equals 1/2 mv2 plus mgy2.
And what did you use for y1?
Didn't that just equal 0?
Yep.
Yeah.
Exactly. Exactly so. And now you have numbers for all of these, except maybe the mass. Are we not told the mass, or are we told the mass?
The true center of mass 2.1 meters across the bar with a speed of 0.7 meters per second.
That was a yes or no question. I wish you got And so here we do have a common factor of n that can be factored out and divided, and there you go. So we end up with this equation, y2 equals 1/2 v2 squared minus 1/2 v1 squared.
Oh, I was supposed to solve for V1.
Oh, I got it, okay. So v1 is equal to root,
V2 squared plus 2 GV2.
So I have a question on that one.
Yep.
So here is that number 36? Yeah, I
Uh-huh.
did that one as well.
Uh-huh.
Did I just- oh wait. Never mind. I had a question on number 38.
38.
That was it.
Yeah, go ahead.
Well, I don't know how to explain it, but this is, if you see here, this is what I get in the end, and this is
Uh-huh.
what they get.
Okay,
I don't understand
the difference between what they did here.
what, because it's pretty much the same thing. Is it a rounding error that I did maybe? It doesn't.
Yours makes sense to me. Yours seems to make sense also. That's not just a rounding error.
Yeah, I know.
That's a difference of about 10%. So, let's take a look. My guess is there's a computational issue right here. So we're looking at number 38, and she does a quick, oh, we just talked about this one. Right.
Oh, really?
We did complete someone.
So we have a projectile fired upward at a 45-degree angle with an initial speed v0. And so you did a before and after kinetic and final chart.
Mm-hmm.
And what was the height of our cliff again?
265.
Meters?
Yeah.
Dang, that's a high cliff. And so your potential energy should be m times 2650.
I did it times 9.8, so and it's 25.
Mhm. $25.97 is fine, yep. With the 9.80. And the kinetic energy, you have 0 here. 0 is actually incorrect.
Oh, no, it's that's potential.
Oh, that's potential. But the potential before is not 0. The potential before is
I put
up here
0
at
at the bottom, or at the, I guess, well, here's how I drew it, so maybe it's the way I drew it.
Uh-huh.
I put 0 here. And this, I didn't realize, so if it were at a,
Yes. Isn't it starting at the top of the cliff?
then
I think it's starting at the top of the cliff is the problem, right?
Yeah. Start up jump. Right. Start up jump.
At an upward angle from the top of the 265 meter cliff. Yeah, so that's the deal, was that your actual visualization of the problem was incorrect. It was being fired from the top of the cliff, and you had it being fired from the bottom of the cliff.
so then that means,
PJ.
Yeah, I haven't figured out. I still get flustered with no ability to remember. That awkward moment when you're trying to delete something and it refuses to
I'm
delete,
not
you
trying to
know?
delete it. I'm gonna,
You can't close it.
Yeah.
and why would you be having apps open if you're not supposed to?
That's Andrew, man. I don't use my iPad in school.
That's not a good thing.
I'm not about that way.
Okay. Okay, so then, with that being said, then now, before is, well, my befores and afters are different, so what would it be? So the potential for before is So it's setting the potential after 0 now. Correct?
Yes, that's right, the potential after the 0.
Okay. And then, so what makes it so that way it now flip-flops? Like, would it not make a difference?
You mean mathematically, would it make a difference?
Yeah, wouldn't it just be the same?
Well, no, actually. So this is the correct chart, right? We have an initial velocity v0, and we have a final velocity v. And so now if we do totals, we find that our 2597 is adding to instead of subtracting from the final total energy right there. So that the result is and actually I'm going to do this because this is the third time today that we've got this. This is really MGH, right? So this is the third time today that we've gotten this result, this exact result.
I just usually just start math if it's gonna work. Like equation, you know, like I want to have mg squared plus mg, but yeah, I usually just jump to that.
You usually do it algebraically, or you jump to this equation right here?
E0 squared, yeah. Is that gonna mess me up or something? Sometimes?
Only as long as you're clear on where it comes from, so that you don't apply it in a situation where it doesn't apply.
Yeah.
Do you know how to change the color of the text?
Yes.
Okay, well, if there are no more questions, we're going to call it a day.